Welcome to the deep dive. Today, we're tackling something absolutely fundamental. The 6 core ways we generate electromotive force, or
Right,
EMFs.
EMF. That's the force that converts some other kind of energy. Could be chemical, heat, light, motion into electrical potential energy. Voltage, basically.
And understanding these 6 methods is, well, it's crucial for anyone in the electrical field, wouldn't you say?
Absolutely essential. I mean, whether you're dealing with huge industrial generators, installing solar panels, or even just understanding the sensors in a device, this knowledge is the bedrock.
So we've looked at some really good training materials, and they kind of break it down nicely. You've got the big ones. Electromagnetic induction, chemical methods like batteries and solar. They're, powering most things and improving fast.
Definitely the big three in terms of scale right now. Then you have the others, maybe less common, but still important, using heat, pressure, and the sort of odd one out, electrostatics.
Okay, so our mission today is to unpack each of these. We'll start with the heavy hitters, magnetism and chemicals that keep the lights on, and then explore those maybe more specialized methods. Sound good?
Sounds like a plan. Let's dive in.
All right, first up, magnetism, or more formally, electromagnetic induction. Generator action. This is the big one, right? Responsible for almost all the electricity on the grid.
Pretty much all of it, yeah. And it boils down to physics specifically, relative motion. You need a conductor moving through a magnetic field or, a magnetic field moving past a conductor. One has to cut across the other.
And the rule governing this is Faraday's law of induction. It says the voltage you get is proportional to the rate you cut those magnetic lines of force.
Exactly. And the number they often cite is cutting 100 million of those lines, or Webers of flux, per second induces exactly 1 volt.
1 volt, which sounds specific.
It is.
Yeah.
But think about what that means for, say, a power plant generator. They need thousands of volts, right? But they can't just spin the generator faster and faster mechanically. That's a huge problem.
Yeah, the whole thing would tear itself apart eventually.
Right. So if you're limited on speed, say 3,600 RPM, which is pretty standard, how do you get that high voltage? You have to max out the other factors in Faraday's law.
Which are?
The strength of the magnetic field, the flux density, and the sheer length of the conductor moving through that field.
Ah, okay. So that's why those power plant generators are absolutely massive.
Yeah.
Huge magnets, tons and tons of copper wire windings.
Precisely. You need immense field strength and miles of wire to get the voltage you need at a manageable speed. It's all about optimizing those 3 factors: speed, field strength, and conductor length.
Makes sense. Okay, moving from motion to chemistry. Batteries and fuel cells. This area is just exploding right now, especially with energy storage becoming so critical.
It really is. So here, the EMFs comes from chemical reactions inside an electrochemical cell. The classic example, and one defined as a constant voltage source, is the lead-acid battery.
Constant voltage, that's key, right? Meaning it tries to maintain its output voltage even as you draw current?
Yes, ideally. You've got 2 different metals, lead for the anode, lead dioxide for the cathode, and they're sitting in a strong sulfuric acid electrolyte. The chemical reaction basically pushes electrons from one plate to the other through the external circuit.
Simple, reliable, been around forever, but then you have lithium ion. Totally different game.
Totally different, much higher energy density, lighter weight. That's why they're in everything portable. The chemistry is more complex, usually a lithium metal oxide cathode and a graphite anode.
And during discharge, the lithium ions actually move through a separator from one electrode to the other.
Right. The separator lets ions pass but blocks electrons. So the electrons have to go through the external circuit, your device, to get to the other side. This movement of ions allows the electrons to free up at the anode.
And charging just runs that process backward.
Exactly. You force electrons back, which pulls the lithium ions back across the separator, and they re-embed themselves into the electrode material. It's a process called intercalation.
Intercalation, like putting little items back into a structure.
Kind of, yeah. The lithium ions are small enough to fit into the crystal structure of the electrodes without messing it up too much. That's why they can cycle so many times. It's quite elegant, really.
It is. Okay, one more in this big category. The fuel cell. Often called a battery you can refill.
That's a good way to put it. Instead of storing energy chemically and then depleting, it continuously converts chemical energy, usually from hydrogen and oxygen, directly into electricity.
So it keeps running as long as you feed it fuel?
Pretty much. You get voltage, current, and the main byproducts are just water and a bit of heat. Very efficient way to generate power continuously from a chemical reaction like controlled combustion.
Okay, we've covered the giants, magnetism, and chemicals. Now let's shift gears to light and heat. These are super important for renewables and sensing. Photoelectric effect first.
Sounds good. The photoelectric effect. This is where light itself, photons, hits a material and knocks electrons loose, creating a current. It's really a child of the semiconductor revolution.
And the main technology here is the solar cell, the photovoltaic cell. The upsides are obvious: no moving parts, silent, no waste.
Long lifespan, too. But the core of it is that PN junction.
Right, the junction. What exactly is happening there?
Okay, so you take a P-type semiconductor, that's one with extra holes where electrons could be, and stick it next to an N-type, which has extra free electrons. Where they meet, electrons and holes combine, creating a depletion zone with a built-in electric field.
And the solar cell design is crucial here, isn't it? The top layer, the N-type, has to be super thin.
Extremely thin, yes. That's so the sunlight can actually penetrate through it and reach that junction, that internal field.
So the light hits the junction, then what?
The light's energy basically breaks apart electron-hole pairs right there at the junction. That internal electric field then acts like a slope, pushing the newly freed electrons towards the N side and the holes towards the P side.
Forcing the electrons to travel through the external circuit to recombine.
Exactly. And that flow is the electric current. The key thing here is that the voltage produced is directly proportional to the intensity of the light hitting it. More light, more voltage.
So a tiny little cell, like maybe a centimeter by 2 centimeters, might only give you, what, 50 milliamps at half a volt?
Something like that, yeah. But because it's proportional, you line up millions of these cells, put them in bright sunlight, and suddenly you're generating significant power. It scales up.
Very cool. Okay, from light, let's jump to heat. Using the Seebeck effect in a thermocouple.
Right, so a thermocouple is fundamentally just two different types of metal wires joined together at 2 points, forming a closed loop.
Just two wires joined. How does that make voltage?
It relies on the different thermoelectric properties of the metals and a temperature difference between the two junctions. You need a hot junction and a cold junction.
Ah, the difference is the key.
Absolutely. If both junctions are the same temperature, nothing happens. But if one is hotter than the other, electrons tend to drift from the hot junction towards the cold junction through one of the metals more readily than the other. This creates a small voltage.
And that voltage is related to the temperature gap.
Yes, it's approximately proportional to the temperature difference, the delta T.
So not really for generating bulk power, I guess.
Not typically, no. The voltages are quite small. But it's incredibly useful and reliable for temperature sensing. Think about industrial ovens, furnaces, even gas appliance safety systems like flame-proofing relays.
Flame-proofing. You mean making sure the pilot light is actually lit.
Exactly. A thermocouple sits in the pilot flame. If the flame is on, hot junction, it generates enough voltage to hold a small gas valve open. If the flame goes out, junction cools down, the voltage drops, and the valve snaps shut. Simple, robust, requires no external power, just relies on that heat difference.
All right, final two. These are maybe a bit more niche. First, pressure or piezoelectricity. Getting voltage just by squeezing certain materials.
Yeah, it's pretty wild. You apply mechanical stress pressure, bending, twisting, to specific non-conductive materials, mostly crystals and some ceramics, and a voltage appears across them.
Quartz is the famous one, right? Silicon dioxide.
That's the classic example. And the voltages can be surprisingly high. The source material gave this example. A tiny 1 centimeter cube of quartz, if you hit it with about 2 kilonewtons of force.
Which is what, like a couple 100 pounds?
Roughly, yeah. That little squeeze can generate something like 12,500 volts.
12,000 volts? From a squeeze? Okay, hold on. If it can make that much voltage, why aren't we, like, paving roads with this stuff to generate power from traffic?
That's the crucial point. It's high voltage, yes, but incredibly low energy. That 12,500 volts is just a momentary spike, like for a microsecond. There's virtually no sustained current behind it.
So it's like a quick electrical flash.
Exactly. You get a big potential difference, but you can't draw significant power, which is voltage times current over time, from it continuously. It's a voltage shock, not a steady power source.
Okay, that makes sense for things like the igniter on a barbecue grill.
Perfect example. You push the button, a little spring-loaded hammer whacks a piezoelectric crystal, generate that instant high voltage spike, which is enough to jump a spark gap and light the gas. Instant mechanical to electrical conversion for a specific task.
Clever. And there's an opposite effect, too.
Yep, the converse piezoelectric effect. Apply a voltage to the crystal, and it physically deforms, changes shape slightly. Useful for things like tiny actuators or even in some analog watch movements to make them tick.
Fascinating. Okay, last one, number 6, electrostatics, usually generated by friction, which they call tribocharging. This seems like the least practical for power.
Commercially, for large-scale power, yes, it's the least used. This is your everyday static electricity. Rubbing two materials together, separating them, like shuffling your feet on a carpet, peeling plastic wrap.
And getting that zap when you touch a doorknob, we've all felt that. You can build up thousands of volts doing that, right? Why doesn't it, seriously hurt you?
It's the same reason as the piezoelectric crystal. Again, high voltage, but extremely low energy. You might have 10,000 volts potential difference between you and the doorknob, but the total amount of charge, the energy stored, is minuscule, maybe tens of microjoules.
Like that analogy you used, a fast train with only one tiny boxcar.
Something like that, yeah. High potential, but very little actual stuff charge to deliver. That tiny bit of energy discharges in a flash, gives you a zap, but it's usually harmless.
But there are machines that use this principle for high voltage, like the Van de Graaff generator.
Absolutely. Those can generate millions of volts, up to maybe 20 million volts. They were historically important in early physics research, like for particle accelerators, atom smashers.
Now, you mentioned something critical here. Batteries and grid power, we called them constant voltage sources. The Van de Graaff is different.
Radically different. This is maybe the most important conceptual distinction we've touched on. Batteries, solar cells, the grid, they try to maintain a constant voltage, and the current changes based on the load you connect.
Right. Your outlet stays at 120 volts, and plugging in a tiny lamp draws less current than plugging in a big heater.
Exactly. The Van de Graaff generator, however, is a constant current device. Its mechanism that moving belt-carrying charge up to the sphere delivers a more or less fixed, very small amount of current, typically microamps, regardless of the load.
So, if the current is fixed, what happens to the voltage?
The voltage varies dramatically depending on the load resistance connected to the sphere. If there's nothing connected, very high resistance, the voltage builds up to those extremely high levels. But if you bring, say, a grounded wand close to it, drastically lowering the resistance,
The voltage plummets.
instantly, it drops to whatever level is needed to push that fixed tiny current through the lower resistance path. It prioritizes maintaining current while the voltage swings wildly. This constant voltage versus constant current behavior is fundamental to understanding how different electrical sources operate.
Hashtag outro. That distinction really ties it all together, doesn't it? We've
Yeah.
gone through 6 ways energy gets converted into EMF. Motion with magnetism, chemical reactions, light hitting a junction, heat differences, mechanical pressure, even friction. 6 different physical processes.
And the really practical takeaway, I think, is understanding that difference between the constant voltage sources we use every day, batteries, grid power, and those specialized constant current sources like the Van de Graaff. Their behavior under load is completely opposite, which impacts everything from design to safety.
And it all hinges on these proportional relationships. We talked about voltage linked to the rate of flux cutting or the amount of light or the temperature difference. It's all
Yeah,
physics.
that's-
So, thinking about the future. We mentioned that chemical storage, batteries, and solar technology are advancing incredibly fast. Given those trends and the physics we've discussed, here's something for you, our listeners, to think about. Which of these 6 methods do you believe holds the most promise for future large-scale sustainable energy storage if we can overcome the current engineering hurdles? Is it refining chemicals, making light conversion even more efficient, or something else entirely?
That's a great question to ponder. Lots of potential, lots of challenges.
Definitely something to mull over. That's all for this deep dive. Thanks for joining us.